very good. Welcome to this is our fourth class now. So the first class was a little bit of an orientation, had a little bit about my and the school's philosophy of education. Okay, the idea that innovation comes about by integrated multidisciplinary study. Okay, doesn't mean that you. Okay, I have to share. Sorry. Okay. It doesn't mean you know just a tiny bit of everything, but it means you are deep in selected area. Okay, but they're not, they're not very closely related area. It's not like you dig deep in French and well, if you dig deep in, let's say, Italian and Spanish. Okay, those are two closely related language. So it would be something like Chinese and French or something like that. So it's that sort of thing when you have a cross-pollination of idea. And I think last week I did mention the the Black-Scholes equation, which indeed won the innovator or the professor who came with the equation, the Nobel Prize. And it turns out that the mathematics behind it is not that complicated. It's simple. It's actually second year engineering mathematics. But before you get to that mathematics, the insight across so many areas, something more abstract in mathematics, but certainly idea that comes across from trying to understand the dynamic of financial market and so forth, right? So you have that's the philosophy we're talking about. And as you need convincing, today, this class, this pre-course, is about teaching you mathematics, but in a way that uses interactive programming. In this case, the Mathematica program as sort of like a go-between. Okay, go between the concept, go between what you want to do, go between what you want to express mathematically, and this idea that you use Mathematica to communicate is very powerful because it also has very powerful visualization. Okay, so we have this undergraduate lab, right, on the fourth floor. You can have like a 3D printer. You can create your own ideas, express it as a 3D geometric a model in Mathematica, and then you can send it to printer and it prints out something. Okay, but even before you print it in 3D, you can visualize, rotate it however you like in the program. Okay, good. Today I thought I'll start with something I thought might be a little bit fun exercise. How many ways can you add two things together? Okay, I played with it yesterday, and I think I came up with about 10 different ways. Okay, so let's do this. So delete all output. Okay, right. Okay, so you can follow through with your keystroke if you like. Can you see? Obviously, the most obvious thing you can do is A plus B, right? Okay, so let's do that. Yeah, nothing interesting there. Okay, we did that. That's what you've been doing since kindergarten. Okay, now I want you to understand that in this context, you have to think of it not as a real operation. Mathematically, that's the operation. But in a computer, you have to think of it as it's actually a shorthand for calling a function. Okay, so this is actually thinking of A plus B in a full-fledged functional programming. You're calling a function. That function happens to expect two or more places, and you supply with the argument A and B, and then you get that, right? So you're not adding A plus B, you're calling a function called plus. That function happens to expect two, maybe more, but if you supply it with two arguments, A and B, separated by a comma, see? Separated by a comma, then it gives you the result. Okay, so that's the second way. Let's go through this quickly. More computationally, and this is to get you to the idea of mathematics as an, programming as an algorithm, okay? When you add two A and B, there's kind of like intermediate memory, intermediate state, where you memorize first what the value of A is, then you add the value of B to something, and then you keep it. So this is the idea of creating quote unquote a temp variable. Again, this is complete overkill. This is riding an elephant to catch a bug, right? So you do this and within a construct called module, right? Module has this local, okay? Module has two things. The first part is a local variable. In this case, I define it with temp, okay? And immediately I assign it the value that I wanted, a plus b. And then what's the function? What do I want to do with it? I just want to spell it out, okay? So internally, I create this, and then I send it. Good thing about this is that there is no, in programming, it's called side effect. In other words, you don't have to worry about having assigned the word temp to a value, okay? This is completely clean. It creates a value of temp just for this job. Once you execute it, it's gone. It's gone. So there's no possibility of error. A lot of time, if you do something like this, like temp equal to A, right? And then temp is equal to A plus B, say something like that, right? Later on, you might want to play with temp just for no reason. The temp has a value already built in A and B, and you forgot all about it already, okay? So this is not a clean way of doing things. So this is a very nice, module is a very nice way of compartmentalizing, okay? Get into the habit of this, get into the habit of this. By the way, module is the same word that people use in modular thinking, okay? Modular thinking, not the same word as modular arithmetic. That unfortunately is something else. But modular thinking, you know, thinking of things as component, breaking down into little cells. That's very powerful in design thinking language, right? So this is even more elaborate. Okay, create a temp, but don't assign a value to it. Assign it in here, assign it here, and assign it here. So that's, you know, very long-winded way of doing A plus B. Of course, once you have this will be exactly how more advanced stuff, like, you know, neural network or whatever. Now, this is a second way of functional programming input, right? This is the monkey see, monkey do thing. So instead of defining a function, okay, use a built-in function, you define it yourself, but you define it once. You show the argument what you want done. What do I want to do? I want to do this operation. Take the first thing and add the second thing, and this is the signature that say it's an inline function. It's called inline function. So adding A and B using inline function. This is what I want to do. Now apply it to that. Same result, right? Same result, but same thing here. You can use that as well. You have a built-in function, but now you make it a pattern. A pattern is to supply with the first guy and the second guy. So nobody wants to do this in real life, but it's certainly valid, okay? Now, here comes the thing. User-defined function. This is where you actually define the thing itself. Sure. Actually, that's a good idea. Yeah. So what you want to do is define a function. Now, this function is completely silly, right? Just u plus v. Notice that when I call it to a plus and b, right? But when I define it in a different thing. It could be a and b, it could be x and y. The point is, this thing is a placeholder. This thing is a placeholder. So that's how you define a function, okay? So once again, this is how you communicate with computer. Throughout your undergraduate career, the underscore is to say that it's a generic match. Find anything that matches this, okay? So this is, otherwise it would interpret it as a particular value of v, okay? So this underscore in computer, if you talk to your friends from computing department, it's called something like regular expression matching, okay? It's like a joker. You can play card, right? A joker can be anything, right? Can represent anything. Yeah, exactly. So you can supply it with anything. So if I did this, I get that. But the good thing is you can use it again and again. Yeah. Oh, this is yeah. What's the difference between this? This you define. This you also define, right? Well, in usage, in practical usage, the difference is this. whenever I want some operation, just quickly, I do it once. And I don't want to clutter up the whole definition. I don't want to have like a big definition of the function. I would use this. So I define it. I want this done. Do it. I'm not going to use it again. I'm not going to do this very often. Okay. That happens a lot when you're exploring data. Okay. You just want to say, well, let's take the third column and maybe multiply by 2, see compared to the second column, see what happened. Okay. But this is not something you want to do all the time. So you don't want to define it and give it a name. Okay. When you give something a name, that means it's a kind of permanent thing. Okay. So obviously this is a bit silly, right? Why would you define u plus v? Because it's already built in. In reality, what's going to happen is you're going to be defining your own algorithm, and this can have 1,000 lines. Okay. In reality, that's okay. Once you get to something very complicated, procedural, right? It doesn't make sense to do inline definition anymore because you want to name it. You want to do it once. So this is like making a quiche or something. Okay. If you're just going to break an egg, you can use inline function. If you want to make tom yam kung or something elaborate, you want to define a whole bunch of steps. That's what you want to do. Okay. So you use this user defined function. Right. Okay. Good thing about this class is you kind of like jumping back interchangeably between mathematical thinking and computational thinking. That's what I want you to do. In the future, you're going to be jumping back and forth between text thinking and picture thinking. That's another discipline in the curriculum. Right. So here's a thing that I haven't told you before. Not only can you pass value as argument, you can literally pass a function as an argument. What I mean is this. Here's my function. Okay. My function is to do something to 2 things. So I have to supply with the 2 things I want to do it, but I actually haven't specified ahead of time what I want done. Yeah, I haven't specified ahead of time. Literally, the function itself becomes an argument. So if I define this, okay, and then I call it, I get the same thing as before. Do this to 2 things. What is this thing that I want to do? I want to do plus. I want to do #1 plus #2. I want to do add 2 things. I want to do this module thing. Exactly the same thing, right? It's the same thing. Okay. So see the level of sophistication, right? So let's progress. Let's review a little bit. Okay. This is what you want to do. This is the bug you want to catch. Okay. You start to write a small, you realize that actually implicitly you're doing something more complicated, which is to call a function named plus and then supplying it with A and B. Okay. You can do it in a way that's sort of like localized thing. Okay, that's module. So you have this thing, you know this thing, you know about inline function. Now I define something else. I define generic operation. So anytime I want to do a thing to 2 things. Okay, so maybe in the future, let's say I am well, I'm not Christian, but let's say I'm a priest, a Christian priest, right? I can say do this to 2 things, okay? And the function is bless the marriage and then apply to Bob and Alice, okay? Something like that. So what's going to happen? It's going to call a function called bless the marriage of Bob and Alice, okay? So this is completely generic, okay? And this is very important because you know, you're starting with number, you're doing in the future, this can be a text, right? Right. So this could be something like, and this is a little bit ahead of the class, but let's say you can have some kind of a text file. Okay. Text file that say something like describe emotion. Okay. You can say describe emotion, and then you give it a picture file. Picture of my cat, okay, and make the subject look sad, right? And this is style transfer. You use this in machine learning. So this is some kind of a text that has a meaning. Okay. So this is a filter. I want to make this picture look sad. I take this emotion plus cat equal to picture of sad cat. Okay. So this can be very generic. Okay. So again, so that's why we are riding an elephant, because the elephant is going to be able to do all sort of things throughout your life. But I'm just showing silly example for now. Okay. Yep. So you can do all kind of stuff, and so add module inside, doesn't matter. So this is. So you get the point. You get the point that the more complicated a way of doing a simple things. Okay, the more maneuver you can do with the elephant to catch just a tiny bug. Later on, you ride the elephant to catch a big tiger or something. Okay, that's the spirit. Anyway, so let's get back to last Friday, right? On Friday, we start to talk seriously about linear algebra. And again, what are linear algebra? What is linear algebra? Well, the concept of algebra is you do something to maybe a pair. You get vector and you multiply to the dot product to another vector of dimension 5, you get the sum product, and that becomes a scalar. Okay, so internet connection stable. Oh, never mind. Okay, so let's think of what we've got. Remember, we've got scalar, vector, matrix. Eventually, you get answer, but not in this class. Okay, so scalar is a number. For example, here's a funny number. Okay, n gives a number. Okay, I can literally do this, by the way, because it recognizes. First, y length x is m, so you can add them. So this is the option. I put note in blue. The example is not blue. Okay, the note is in blue. You can perform element-wise vector addition in two vectors of the same dimension. The product it produces a scalar. See, x1 y1 plus x2 y2. So this is like a mathematical version of doing a sum product. Now here's something. This is going to be again, if you data science, this is one of the most useful my project to investigate whether or not companies that have let's say two companies, right, are separately registered, but in fact connected because they share the same owner or director. Okay, and we do that sometime, and this is something you should not do. Let's say I'm the owner of two companies that are separately listed. Okay, but I control both of them. What I do is this guy has a lot of tax. This one has a high tax. This one has a low tax. So I artificially make this one profitable and make this one making a loss, even though actually all the money comes to me at the end of the day, right? I just make this look profitable. Right? So the department of the revenue department wants data scientists to look at this and how can you figure out and things like that. Well, it turns out if I have a matrix that maps between who owns which company and I perform this kind of operation, I can actually trace relationship between company. Okay, so I use this in a project. Okay, project that's real life. But I want to show you what this function is. This function is called inner. Now, you remember that the dot product, what does it do? it sums the word is times. So you take x1 times 1, and then you plus x2 times y2 plus x3 times y3. So in fact, okay, x dot y, which is this, is the same thing as what's called inner product. Exact same thing. Okay. Now, why would you learn about the inner product? Once again, you're riding an elephant to catch a bug, right? So instead of doing this the easy way, I do the hard way. It's an inner operation between x and y. First, I take x plus y and then add them together. The reason I can do that, the reason I want to do this difficult way is because, well, later on, like in my project, I don't want to do plus, I don't want to do times. If I reverse order of all else, so this is x1 plus x2 times y1. Out of the sudden, this is opposite now. This is completely different operation. Okay, operation. Yes, power. These are all different things. I just want you to do, technically, this is called an inner operation. The inner operation is extremely powerful. Okay. In my own thesis, I use something like this, by the way. I use this, but I didn't use Mathematica back then. I used C++. When I was your age, you know, C++ was all the rage. Actually, calculate this. My solution, well, never mind. My solution it's a multi. So this is like the number of parameter per model. This is the number of model of the class. This is the number of parameter per the other class of model. This is the number of models and how they use together. So I actually use this in my thesis. But in the I think the operation I have between the shareholder and the company, I think is something like take the left or something and then add. Okay. Now, here's an interesting thing, right? Here's an interesting thing. What if I multiply x by itself? What's a dot product of x by itself? Now, let's make this, let's make a special x. Okay, my special x. My special x is, let's call it v, okay? V is equal to something that is 5 inches long, y, 4 inches long, and 3 inches high. Okay. Anybody knows what I'm getting at? Oh, let's try something else. Let's make it not obvious. 5 and 12. Anybody? Right. I'm going to Pythagorean theorem, right? So what is, okay, if this is my v, this is my v, right? This is my v. Okay. By the way, if I write another line, okay, v dot v, it's just gonna do both, right? But let me show you first what's gonna happen. Okay, see, the first line is an output. The second line is an output. Sometimes I don't want the intermediate step. So what I do is I put semicolon. Okay, this is a language primitive. It's just saying that do this, but you know, keep it and then do something else and then just show the last one. Okay. Now, anybody know what this means? Okay, let's take square root of this guy. Now, square root, I don't know how to write the square root. So let's go to there, square root, right? So let's do this. Square root. Oops. Silly. This, I don't like this keyboard at all. Okay, 13, right? Why? Because 5 square plus 12 square is equal to 169, which is 13 square. So, okay, you can look at my, something is 5 inches tall 12 inches wide, it's going to have the diagonal of exactly 13. That's Pythagorean theorem, right? So wait a minute. If I have something called a vector, and that vector has number 5 and 12, that means 5 is, okay, sorry, I should put it that way. 5 is my x coordinate, right? My horizontal coordinate. Y is my vertical coordinate, right? The vector itself is here, right? Right? The vector itself is here. So what's 13? It's actually the length. So you have this dot product. Anytime you dot product the thing with itself and take the square root, you actually get the Pythagorean length. Okay, it's called Euclidean distance, but Euclidean geometry. But anyway, that's that you get, right? So this is like if I go to the east, let's say I go to the 59 miles, 57 miles, and I go north or go south, minus 312 miles. The point is how, so let's say this is a road, right? You have to go this kind of squarish thing, but you can take a helicopter. So what's the distance? Well, the distance is actually this. Well, let's make it numerical. So, right? 317 miles. So this is actually the length of vector V. Okay. So what's the formula for it? And this is what I want to tell you. Formula for it is x squared. The first, okay, I have just x1 and x2, right? So the first thing square plus the second thing square, right? Because it's a dot product with itself. So it's not x1 times y1, it's x1 times x1 plus x2 times x2. So that's this, right? Well, technically, this corresponds to what mathematicians call a norm. Okay, so this thing is the same thing. If I go this 5, go up 12, it's the same thing as going diagonal 13 in that dimension, right? That's Pythagorean theorem. But that also means that 13 is the length of the vector that I 0, 0 to 5 and 12. It's the same thing. Well, this thing, in terms of the formula, is to take 5 square plus 12 square and take the square root. Notice there's always the word square. Well, that word is corresponding to what's called 2. 2 is take to the power 2, take to the power 2, and take root 2. Okay? Now, mathematician will you take the length is not negative, right? So instead of take to the power 2, let's go to x. Let's say norm x, yeah, is equal to this, right? Now, the absolute value function is in it just to make sure that it doesn't go to negative. But for power 2, it's already non-negative, okay? The point is, here's where you can make it more fun. Instead of taking the second power and take the square root, you can take 7th power and take the 7th root. Okay. And because 7 is an odd number, right? Negative can become negative. That's why you need the absolute. So this is it. This is a value. This is a perfectly valid way of measuring distance. So if you are in, you guys been to New York City? New York City is like a grid, right? So if you want to go, 3 Avenue East, then 4th Street up, right? You have to do that, right? If you have a helicopter, it's 7. But you live in Manhattan, you don't have a helicopter, you walk, okay? So you go like this. So you take the absolute value of 3 plus absolute value of 4, that's 7. That's why one norm is known colloquially as Manhattan norm, okay? Whereas second power, Euclidean norm, it's like you have a helicopter. So it's called helicopter norm, okay? So this is 2 norm, Two norm is also known as helicopter norm. One norm is also known as Manhattan norm. Okay. Now, let's be more fun. What if I do this? Can I do this? 1,000th norm. Can I do that? Anybody see what happened there? If I take x1 to the power infinity and x2 to the power infinity, and I take the infinity root, what's going to happen is that it's going to give more the secret to this. See, simple that. Now, why does it matter? Well, the length is how you measure things. Okay, and you can see right in Arkansas, okay, just nothing but flat land, nothing but flat land. You run across as if you were a helicopter. But if you live in New York City, you can't. You have to go horizontal. It's a mix between all of this. So, you know, this happens in real life, by the way. So mathematics accommodates. It doesn't matter what reality. You know, my friend lives 3 blocks east and then 4 street up. I can't just take a. Okay, so mathematics is always to serve you. So anyway, so that's another thing. Up. The frame. Yeah. So see, that's x1, right? x1, x2. The last one is 3 and 4. So that's the one Pythagorean. So it's the distance, right? So that's a 2 norm is the same thing as dot product and then take square root. Okay, so that's the same thing, right? So that's a Pythagorean. But if you take a helicopter norm, it's 7. If you take infinity norm, it is 4. Okay, it is 4. Think about it. I was trying to measure the length of something that is 3 units to the east, 4 units up, or sorry, 5 to the east and 12 up. That thing is 13, right? Well, I can think of it not as the length of a vector. I can think of it as the distance between 2 vectors. One vector sits at 0 and 0. The other one vector sits at 5 and 12. So instead of saying that this is the length of vector, I'm saying this is the distance between this point. Okay. So instead of doing this, for it is Euclidean distance. Okay. So you can measure Euclidean distance. Anyway, right away, all this is going to be part of your vocabulary. Whenever you deal with data, you're going to have a bunch of numbers. Okay, a bunch of numbers. And again, a logistic is a good example. A lot of time where you don't use an obvious norm, you use Manhattan norm, something like that. Like when you're trying to measure how much of a cutting you have to do, something like that. Okay, now let's go to a matrix. Well, a matrix in Mathematica is nothing more than a list of lists, right? Right? So if I let's do this guy. So it's a list of lists, B, C, D. Okay. Now it doesn't look nice like this. So let's make it look nice. To make it look nice, what do I do? Matrix form. Right? A, B, C, D. Okay. So it's a list of lists. Now, how do I construct it? Obviously, there are many ways, right? I can use array, I can use table, or I can manually do it. Now I want you to focus on this. Okay, I want a matrix that is 2 row and 3 column. Okay. One way of doing it is to write it as a list of lists. So this is very manual intensive, right? I have to keep everything. So it's a list of, what's the first list? A11, A12, A13. What's the second list? A21, A22, A23. So this is okay as well. This, okay. This is one way of doing it. Yeah, it's a list of list. Another way of doing it is to use array of A, and I give the dimension 2 by 3. Another way of doing it is table. Okay, remember array and table are similar, except a table is uses an index. So instead of going implicitly 2 by 3, I say A, I, J, I to 2 and J to 3. Okay, now sometime you don't want and then another table of table. This also useful because row and column. Okay, but at the end of the day, this is writing an elephant but I'm just assigning a placeholder for 6 value. Okay, I want 6 value. Okay, I want 6 value that can be accessed using 2 index. So 6 value is going to be stored in an Excel. It will be a table, 2 row and 3 column. Okay, how do I do it? I can do it manually. I can do it with array and specify the dimension. I can use the table, specify the dimension, but also the index. I can use table, but in this case, it's a table of table rather than a rectangle. It's the same thing. Okay, I don't want the writing, but all I want to say is the same thing. Same thing. That's a matrix. So the dimension is what gives the row and height. Okay. So yeah, let's finish with the dimension and you can go. So the dimension gives you exactly that, right? Once you created something, the dimension gives you the number of row and column in that order. So if I created, so the dimension of this, so if I create an array, and 7, that's going to be too long to, it's too huge, right? And I just say, what's the dimension of that? Well, sometimes you don't create it. Sometimes, a lot of time I read this from Excel sheet, read it from CSV, read it from my client, read it from input. Okay, so I use this. Okay, Cup. Let's take 2 minutes or 3 minutes, and we'll come back. Array and list. Yeah, array is a way of constructing list, right? Except it's easier because list say that it's an order thing, right? You can manually enter it, or you can ask the computer to construct it. So my instruction is to say, give me a list of 5 things that can be referenced by the word A. So I say it's an array of 5. See? So this is how I do it. So I make so let's call it array of U and 7, right? So it becomes U1, U2, U3, U4, U5, U7, right? So this becomes a way of naming a variable. So all 7 of U equal to this. Okay. So I can refer to individual. I want to take the 5th guy, right? Array is a way of creating a list. Yeah. Because you can type this by hand as well, right? If you don't use a function array, type this by hand. Okay. The point is, if it's 1,000, okay. Norm is a distance. Okay. Pythagorean is only 2 norm. Because Pythagorean use Euclidean geometry. So Pythagorean is equal to 2 norm. 2 norm. 1 norm is Manhattan norm. So Manhattan norm is when you take the absolute distance in both directions. Helicopter norm is when you take the shortcut, the shortcut. So helicopter norm, Euclidean norm, Pythagorean norm is the same thing. ไม่เหมือนกัน depends on your application. Norm is คำสั่ง with way of specifying. So how do I measure distance? I want to measure distance by taking individual coordinate. I want to take distance by taking individual coordinate square. I want to take the distance by individual coordinate to the power 7. Right? I can do that. I can do that. I can do that. And the reason here. It's nothing. But notice, guys, notice. When I to all I'm saying is that give me something that has a name A that has 2 rows and 3 columns. So that's it. That's all it could do. Now, what if I want something that's more intricate, like a function depending on position? Right? Watch this. Watch this. That's when I need I and J. So instead of naming it A and IJ, I can do this. Say something like I plus J. Okay. I can do that, right? Now, could you do that with array function? You can't, because array doesn't have index. It doesn't know how to manipulate with index. Now, if I did this, I get that, right? So it's actually take the number of row plus the number of column, or I can do something else. I can say A to the power J. Okay. Oops. J. See? Right? So what I mean is that with table, it's a lot more powerful because you have a name of I for the row and J for the column. So you can specify what you want to do for particular position. Now, this is even more powerful because you can do something along the row. You can do something along the column. That's very different. Okay, so I tend to use this a lot. Table of table. Okay. So don't worry, guys, that you see something that looks a bit silly. It is silly. I know it is silly. Okay, but it's not silly because it's more powerful. There's our occasion where you can just use this. I just want a placeholder. Think of array as just a placeholder. But table, table is equivalent in Mathematica to list comprehension. Okay, so remember that. What? Yeah, this is the same thing. This is the same thing. All the same thing. This the same as this, same as this, same as this. Okay, but obviously, if I change it, then it wouldn't be the same. Okay. Right. Okay, so now we have the matrix. Okay. Now you got scalar, you go to vector, you go to matrix, then you go back to vector and say, well, if a vector is a stack, a vertical stack of number, right? An array is a rectangular, a matrix is a rectangular array of number. Well, what if that rectangular array only has 1 column? It looks the same thing as a vector. And in fact, you're right. You're right. Okay. So, see, think of this as a column vector. Now it has a dimension 3 by 1. Okay. So a 3 by 1 matrix is the same thing as a vector of dimension 3. However, Whereas vector have something like this. Now watch this. It's going to get error. Anybody knows why? Dimension doesn't match. I have to take one of them into a row vector. I can do this. If I did this, by the way, watch this. Now it becomes a row vector. Now I can do it. Or I can transpose it. Transpose is one column. So I can do this, get the same thing. See that? So this here is a 3x1 matrix. This one is a 1x3 matrix. So they get along okay. Yeah. 3x1, 1x3, 3x1, they get along, they multiply. You get this. Or you can say this is 3x1. I take the transpose. Okay. So this is what 3x1 looks like in your mind. Looks like this, right? In fact, let's say A, B, C. Okay. But if I do this and I take transpose, okay, it looks like this. That's why in the math textbook, so that's that. So what you can do, you can certainly add matrix of same dimension. Again, just as the vector has to be the same length, right? You can add two matrices. Because they don't match. Okay, just think of table that has precise number of row, precise number of columns. Okay. Now, okay, the interesting thing is, okay, you can do this. You can add, oops, okay, this thing here. You can scalar multiply matrix. You can element-wise subtraction. I'm not going to write it down here. But the interesting thing now is that you can multiply two matrices together, right? Right? So, anybody see this? And I'm just going to make a very short introduction. So this is a row vector, right? And a row vector. So this is a row vector times column vector, right? And it gets you scalar, which is dimensional by 1. Anyway, so notice this is what happened. This is an array of what dimension, guys. I can do this on an exam. You don't need a computer. You can use your eye. This is a dimension. What dimension is this? 11 by 22. What's this guy? What's this guy's dimension? 22 by 33. So 11 by 22 times 22 by 33 gets you 11 by 33, right? See? So it's the middle dimension that has to match. So yeah. 11 row, 12 column, 22 row, 33 columns. Yeah. It's the middle one that has to match. Okay, this can be anything. Yeah. So this is, remember last on Friday, I used the word industrial multiplication, right? Do this here, do this, put it here, do this, put it here. Let's make it a battery. A battery is like that, okay? We have a stack of things called battery. Okay. All right. Well, how does it look like? Well, you can see. Well, this is too big. So let's say. Okay. Let's see what it looks like. Matrix form. Oops, sorry. What it did, it thought that you apply matrix form to the last one. So oh yeah, that's right. This is correct. Okay. So it's hard to see right now, but see 1, 2, 3, 4, 5, 6, 7. So it's 3 by 3. Okay. So it works. Okay. Right. Now, I'm going to introduce to you the most important thing. Now, this is, so far we've been playing around. This is where you get to solve equation. Okay. When you were a kid, I don't know if you have this rhyme, 3 สมการ 3 แปร or, four equation and 4 unknown. You always have the same number, right? You can never say 4 equation in 5 unknown. Well, this, strictly speaking, is not true, but it's what we're talking about. You're trying to solve system of equation. There are as many equations as there are unknown. Okay, but we'll tell you why that's the case. Okay, so I'm gonna stop this. I literally will go to something that is now the most useful thing that you will actually use. Okay, so let's start with this. Okay, picture in your mind, 2 equations into unknown, right? 2 equations into 2 unknowns. This is one equation. Okay, this is one equation. Okay, this thing is equal to, well, I don't want to waste time. Basically, you have 2 equations into unknown. A1 1 x1 plus A1 2 x2 is equal to 2 equations into unknown. Okay, A1 1 x1 plus A1 2 x2 is equal to B1. So this is one equation. This is one equation, right? A21 x1 plus A22 x2 is equal to B2. Okay, 2 equations, 2 unknown. Okay, now you can put any number, 3, 5, 7, 9, whatever, I don't care. Okay, we are going to do this generically. Now in Mathematica, it can actually solve equation for you. It's pretty cool. It's pretty cool. Symbolically, just say solve this equation. Now, because it's an equation that you have to, it's not an assignment, use double equation. Okay, so I want to do this. I want to solve 2 equations. Solve this equation for this variable. Solve this equation for this variable. Okay, Mathematica can do this for you. But if I were to do this equation, I do get result. But look at the result. Is it useful to you? X1 is equal to this. But this one is x2. So you go look, what's x2? Well, x2 is equal to this. Wait, but it has x1. So this is true, but it's not useful, right? It's not simultaneous. Okay, so I have 2 equations, 2 unknown, and I solve them. Does it work? Well, in a way it is. It's not incorrect. The solution is correct. This is completely correct. But you're not going to get any closer to the truth, because in reality, what is, you have the number for A11, A12, A1, A22, B1, and B2. What you want to do is get the number for X, right? But this is self-referential. X1 is given in terms of X is given as 1. The reason it doesn't work is because two equations in two unknown, but not simultaneously solved. What you need to do now, you can get around it, but I'm going to forget this. This one is a little bit complicated. But the right way to do it is to do this. Think of this as a matrix. So you write A11, A12, A21, A22. Question is AX equal to B, right? And then solve for this. Now your solution works. You solve for X1 strictly in terms of the parameter of the problem, right? So in real life, okay, this is going to be numbered like 7, 8, 9, whatever, okay? But notice X1 is not given in terms of X2. It's given in terms of number that you can solve. So you get a solution. The reason this works and this doesn't work because here you're solving two equations separately, independently, right? So the information is not added together. In this case, you're solving a connected system. That's why it's called system of equations. The word system comes from the fact that it has to be solved simultaneously. You can't solve for X1 and X2 independently. Yeah. Now you can do what's called back substitution, by the way, which is, take this, X2 is equal to this, put it in here for X1. Once you get X1 back, okay, that's what this thing is. It's back substitution, okay? But that's a little bit horrendous. The point is, with linear algebra, nobody does back substitution anymore. Can you imagine if you have to do back substitution for 1,000 variables? You're going to die first, okay? So what linear algebra is allowing you to do is allowing you to solve system of 5,000 equations in 5,000 unknown in milliseconds, okay? And that's the power of linear algebra, okay? That's the power of linear algebra. Now, I want to show you, okay? Now, this is something that I wrote so to explain, but don't worry about it. It looks a little bit difficult, okay? But the point is this, okay? My A1, A2, A11, A12, B21, B22, they're nothing but description of a line, okay? So the top equation just gives you a line. That's called equation 1. Okay. So this, by the way, okay, when you are in grade school, right? Y is equal to mx plus b. Well, it's the same thing as a11 x1 plus a22 x1 equal to b1, right? It has 3 numbers and 2 variables, right? Except I call it here, it's x1, x2. In grade school, it's y and x. And the slope is m. Here, the slope is not m, right? But it's the same thing, right? So this is the top line. This is the second line. Now, do you understand what I meant by you don't get anything useful? Because you don't get x1 and x2. You get x1 in terms of x2. You get x1 in terms of x2. Likewise, over here, yeah, this is y is mx plus b. x1 in terms of x2. But when you solve them together simultaneously, they have to intersect. Okay? Now, I want you to pay attention to this, and this is going to stay with you for life. Okay? This defines every single thing you will find in life. In life, there are 3 situations. In life, there are 3 situations. Okay? 1, you have a unique solution. Okay? That means X, you have two lines across each other, right? I want something on the blue. I want something on the yellow. How many solutions have you got? 1. That's one situation in life. You have a solution, the solution. Okay? Here's a situation in life. This is another situation in life. What's the situation? Want something to be on the blue line and on the yellow line. The blue line and yellow line never cross. What happens? No solution. No solution. Okay. Now, what's another situation? The other situation is this. You have infinitely many solutions. Because even though you have two requirements, the two requirements are exactly the same. So they actually describe the same line. So for example, if A11, you have A11, A21. A21 is like 3 times of A11. And A22 is like 3 times of A12. And B2 is like 3 times of B1. You're actually copying the same equation, right? It's nonsense. Okay. Now, let me ask you this question, and this is a trick question. When you were in grade school, your teacher never gave you this. Never gave you this. Your teacher will always give you something that's a little bit like that. Okay, that's why you have this rhyme in grade school. 3 สมการ 3 ตัวแปร 3 equations in 3 unknown. Okay? This works in any dimension. It's the same concept. Exact same concept. In 3 dimension, that's what this is. In 3 dimension, you have 3 pieces of equation. The first equation describes 1 variable in terms of the other 2 or the other 3, and they kind of like cross. So if the problem is carefully designed, the 3 equations in 3 unknown will intersect at 1 point. You have the first 2 equations, let's say the blue equation and the green equation. Blue equation and green equation intersect at a line. But that's not unique, right? Because it's still infinitely many solutions. So you have a third equation that comes in and cuts across that. So becomes a unique. Okay, that's it. That's it. All of linear algebra, most of linear algebra, okay? Linear algebra deals with, arbitrary dimension, 3 by 7, 7 by 9. When you work with neural network, you're going to have matrix of so many neurons, 1,000 neuron by 78 neuron in one layer, and then 35 neuron by 45 in the other layers, all kind of dimension. But in physical reality, you just deal with 3 dimension, right? But the point is, the situation you tend to deal with in terms of system of equation, this is applying linear algebra to solve system of equation, you will have A that is a square matrix, right? Because the number of row is the number of equation. The number of column is the number of variable. Think about it. Number of row in this AX is equal to B. Number of row is the number of equation. Number of column is the number of variable. So because you have to have matching number of equation and number of variable at the minimum, you have a square matrix. So that's why a square matrix is studied to whatever infinite degree. There's like a whole mathematics devoted to studying square matrix. Okay, so linear algebra is like this. You have a lot of textbook in linear algebra and matrix algebra. You also have a lot of books that just deal with square matrix. Well, not quite, but you have a lot of theorem that deals with square matrix. And all the theorem, and you can talk to your friend in engineering, they talk about condition of a matrix, determinant, invert, invertible, rank, all kind of stuff. Ultimately, what it comes down to is telling you without drawing the picture and in a way that applies to 1,000 dimension, what situation you are in. There are actually 3 situations in life. You either have a unique solution or no solution or infinitely many solutions. Okay, all the matrix theory again with square matrix that deal with square matrix just tells you about situation like this. In fact, even non-square matrix deal with this. So this is a little kind of app that I make up just to play around with this. And so if you notice that this is this little widget here just sort of like set up the coefficient. So if I set the two coefficient to be the same, have them sort of like mirror one another, they'll be kind of parallel. Okay, so anyway, here's a not trick question, but common sense. What do you think is the most situation in life? No solution, one solution, infinitely many solutions. That's right. Why? Because nobody pays you to analyze the problem if it has one solution. Okay? And also if it has no solution, you don't analyze it, you're done, right? Now, in real life, you do something else, like you kind of relax conditions so that no solution becomes one solution or infinitely many solutions. But in the final analysis, chances are you will not deal with situation with no solution. That's not life. Okay, you give up. Also, one solution, which is the solution you see in grade school, is not life. Because if there's only one solution to a business decision making, to pricing equation, to setting marketing strategy, nobody's going to pay you to do it. Because there's only one solution, right? The reason you are an analyst of any kind is to narrow down amongst infinitely many solutions, which one is somehow best. Okay, and that gets you to the concept of optimization. I'm not going to talk about optimization here. Tomorrow I have you guys have that, right? Tomorrow in the morning, the introduction to applied digital intelligence. I'll talk a little bit about how you can say that applied digital intelligence is a big chunk of it's about machine learning, but there's also a big chunk about optimization. And they kind of like complement one another, okay? But usually optimization is kind of like in the background. That's why you don't hear about it a lot, okay? But within every single machine learning application, there's an optimization, I can tell you that, okay? But just kind of hidden in the background. Anyway, so all I want you to bear in mind, and this is something that I don't care is you never learn anything. Well, I do care. But today, the most important thing is to go home and say, there are actually 3 situations you will face. Situation for which there's no solution, situation for which there's one solution, situation for which there are more than one solution. In this case, infinitely many solutions. Then it becomes your job as an analyst, as a technician, as whatever, to select among the possibilities in the smartest way. Okay. Think about it. I mean, marketing strategy, right? Let's say you want to do something, marketing strategy, design strategy. Well, design, right? How can you design? You design because you have a degree of freedom, right? If somebody tells you, I want you to make a box, right? Go give me a box, okay? Design me a box that is 3 inches long, 4 inches wide, 5 inches tall. What do you design? Nothing. I mean, forget about, surface design. I'm talking about just the object itself. Give me a box, 3 by 4 by 5. Well, that's it. It's 3 by 4 by 5. That's one solution. Okay. So you don't do any kind of design whatsoever. Okay. Now, if I tell you, give me a design for a box that has the volume of 30 cubic inches, but minimize the surface area. Then it turns out in that case, actually there's one solution, but that only comes after you do the optimization. Okay. So this is life. Life is like this, right? You grow up, you never find anyone you like. Okay. That's no solution. Okay. You're born in India, your parents have you assigned to be married to your parents' friend's daughter, let's say, okay? That's one solution. That's one solution. You don't do anything, okay? Most people, in most culture, you have multiple choice. You have many people you meet, then you choose the one that's best for you, okay? That's life. That's like saying you optimize among infinitely many solutions, okay? Well, sometimes not infinite, but so that's that. Now, so this is about system of equation, right? Solving ax is equal to b, solving for x. Last week, if you paid attention, last week, if you paid attention, I talked about computer graphic, right? Yeah. Okay. Well, solving system of equations mean you have something here. That's the result. Ax is equal to b. And you want to solve for x that gets you to b. Okay? That's not going backward. But the very process of multiplying matrix to x, that's a forward process, right? That is like 3D projection. Well, not 3D projection, 3D manipulation. So anytime, okay, let's say I want to move you and I take your location, of the location of your head, okay, in x, y, z, or z coordinate. When I say I want you to move you from here to there, well, I can do something. I can do this. I can say move x this distance, move y this distance, move z this distance. Okay, but this is actually not the way your computer does it. Now that's called translation. Okay, just sort of like slide things. What the computer does is actually have a point from 0, point to your head, and then say, I want this point to go over there. How do I do it? I multiply it with a matrix. I multiply this 3-dimension coordinate by a 3-by-3 matrix, and I move it over there. Okay, that's very, so it's a very different thing, right? It's not translation. It literally is a transformation. And that's what matrix multiplication does in your game. Okay, as far as I know, maybe a lot, sometimes you do addition, but if you do addition, yeah, you can't play with perspective. Just trust me. Okay. So when you do, for example, you know, I'm over here, you over there. Instead of thinking about moving you, think about moving me. When I move over there, how do you look to me over there? That's how matrix multiplication. That's why you can do this 3D graphic, you know, going up and down and all kind of stuff. Okay. Well, anyway, the thing is, that's what you are doing. And we can do this in 2 dimensions and we can do this in 3 dimensions. Okay. Don't worry. Don't worry. This is, again, all you need to know is this. And this is where it might be a good idea to think of the physics definition of vector. This is my x. This is my x. Okay, my x is here. So it is 2 minus 2, but just not drawn right. Okay, I multiply this and I get b. Ax is equal to b. So this is my output. Okay, my input is this, my output is this. Again, this being an algebra, it lives in the same space. I multiply by square matrix, I get something that's in the 2 dimension. I can do this in 3 dimension, 4 dimension. The point is, I multiply x by a. A is a square matrix, okay, of the same dimension as my original dimension, which is 2. Notice that 2 things happen. 1, I rotate or reorient. Okay, so it's pointing to different direction. 2, I shorten it. So the action of a matrix transformation is always twofold. Just as I'm moving your location over there, right? It's changing the direction, but also you're further away from me. Now, can I do just one without or the other? Yes, I can. Yes, I can, right? You're over here. I want you to go further back, but I want you to stay in the same line of sight, right? So that is similar to if I were 0, 0, 0, it's the same thing as scalar multiplication. Because I'm 0, 0, 0, right? You are right now 3, 4, 7. I want you to move back twice as far, but in the same direction. So instead of 3, 4, 7, it becomes 6, 8, 14. So the arrow doesn't change direction, but the magnitude change. Okay. Conversely, I can do rotation like a circle, right? Like an arc, right? So you stay within 2 feet of me. Don't move anywhere. Don't go beyond 2 feet, but move here. Right. I rotate you, but I don't change your magnitude. So matrix multiplication does two things. Okay, it does that. And if you're talking about system of equation, it's kind of like going backward. It's finding the inverse. So with this linear algebra, again, linear algebra, you can have matrix of dimension 7 by 34. I don't care. But in a lot of situations, you deal with square matrix. So you transform X into B or X into Y. Let's say X into Y. You transform X in 8 dimension into Y also in 8 dimension. Okay. So you rotate and you also lengthen or shorten or maybe make it go the other way, direct negative. Okay. So that's transformation. Transform X into Y. Conversely, you can think of, hey, I've got a Y. I want to know which X gave me that. That's like solving system of equation. So that's finding, and the word for it is inverse of A. So what we were doing earlier is actually finding the inverse of A. Okay. And all this detail is it's not something I plan to give you. It's something that I use for my data analytics, because you have to do a lot more matrix. Okay. But essentially that's the power of algebra, except you do this in as many dimensions as you like. Some application requires you to multiply non-square matrix. Okay. Any of you going to apply digital intelligence, going to have to learn machine learning. Okay. Machine learning. Let me give you this. I want to detect cats. Right? Well, what's a cat? Cat's a picture on a screen. What's a picture on a screen? Pixel. What's a pixel? Row and column of values. Now, in this case, because you have 3 colors, it's actually row and column of 3 values. That's why it's called tensor. But never mind. Let's say I have a picture of a black and white cat. Okay. A cat is nothing more than 2-dimension values, 0 and 1. When there's a line, there's a black one, it's 1. When it's white, it's 0. Okay. So what's a cat? Well, you can say that it is a pixel, right? So I have, let's say a 20 by 30 pixel. So what's a cat? A cat is 600 number. 600 zeros and 1. That's a cat. What's a dog? Well, I'm using the same low resolution camera, 200 by 300 pixel. A dog is also another number, another 600 numbers. Okay. Ultimately, I wanted to get to one number. That one number is 1 if it's a cat, 0 if it's a dog. How do you get from 600 to 1? Well, roughly speaking, you multiply it by 1 by 600 matrix. Okay. Well, obviously you don't do it, right? That'd be stupid, right? But that's it. All the neural network you are going to learn is going to be a series of multiplication. There's a lot more intricate step along the way, right? But if you can't multiply matrix, you can't get anywhere in life and in machine learning. Okay. And that's why you have this powerful breakthrough in 2010 about visual recognition was because NVIDIA, had game cards very good at multiplying numbers, right? Multiplying numbers, what? Numbers that represent cats on the screen. You multiply it enough time with certain mathematical transformation, you get to, is it a cat or is it a dog? Okay? And that is the essence of it. Now, ultimately, now this is going to be something very crazy. Think of a cat. Well, instead of think of it as a 600 number. Think of it as an array of number, 200 by 300. Okay, think of it as 200 by 300. Well, that in a way is like a two-dimensional number. Okay, two-dimensional number. Well, if you can represent cat on that, somehow, remember I showed you this auto classify where picture of cats will be together, picture of dogs will be together. That's exactly the same thing. Same thing as words. You can actually gather words that have similar meaning. Sad, unhappy, depressed. That would be kind of like here. And there's word like cheery, happy, best day, beautiful, happy, smiling, be together. Ultimately, you're doing a lot of multiplication so that you can get two-dimensional number over here for the sad word and over here for the happy word and maybe here for not so happy, not so sad, that sort of thing. Okay? So all this is about getting reality into numbers. Okay? And one of the easiest way is multiplication, addition, linear operation, right? Linear operation. But you're not going to do it just for one number. You're going to do it for 1,000 of numbers at once. And that's where linear algebra comes in. Okay? So all the example here, fortunately, you can only visualize, this. But exact same thing that happens here. Okay? All the keywords in here, transpose, inverse, row reduction, all kind of stuff. All this is completely applicable. Now, I'll give you one last thing, which is a word that you might want to get used to. Remember, I talk about the transformation of a vector, right? In, say, 2 dimension into another vector of 2 dimension. And I can rotate and stretch, right? Right? So normally, if you give me a matrix, a 2 by 2 matrix, okay, I apply to any point in space, okay? Or let's say 3 by 3 matrix, okay, 3 by 3 matrix. And I apply to your head. Your head is going to end up moving and stretching. Change the location, change the angle, and change the magnitude. I take somebody else's head, multiply by 3 by 3 matrix. That head will be moved in angle and in distance from 0, distance from me. But you know what? What's funny is that somehow, and this is like a theorem, hidden in here, hidden in there, hidden here, is one student, actually 3, but let's say there's one student. Let's say that one over there. Okay. For some reason, if I multiply this student's head with my 3 by 3 matrix, the result can only be pushed further back or brought closer in, or maybe go in the other direction, but the angle will be the same. Why is that important? Why is that important to find that magic student? Well, think of transformation as any kind of dynamics. Okay? You over here, I move you over there. You over here, I move you over there. You over here, I move you over there. Right? Once you're over there, I move you again, you come over here. Once I move you over here, I move you over there. Right? You just all over the place, right? I can multiply you 8 times and you go all over the place. Now think of one student who belongs to that special character. I multiply the matrix, maybe he goes twice. Multiply again, it goes 3 times. He does not change direction. So this guy is going to grow so fast. Okay, or shrink so fast. Okay, it can go up, go down, or go back and forth, right? It can be negative as well. But it's going to be in the same direction. It's like a sweet spot. In physics, it's called resonance. This direction becomes very important in your problem because it represents a natural response that like there's a sweet spot here. Okay, there's a very important sweet spot. And to make a long story short, and I'm not going to tell you exactly how or why, it's this insight that made Google the most successful search company in the world. Not anything else. Not ads, nothing. It's this. It's precisely this mathematics that allow Google to beat. You were not, maybe you're not old enough for this, but before you were, well, maybe you were born, Google was not the first search engine. It was not the biggest. But within 2 years, it became the biggest and kills everybody. Google killed all other search engine with this mathematics. Okay, I'll tell you later what it is, but okay, it's exactly this mathematic. This mathematic means you take a vector, you transform it, you can only lengthen or shrink or go the other way, but you don't change the direction. You stay in the same direction. In German, the word is Eigen. Eigen means the same. The vector that doesn't change when you multiply by the matrix is called eigenvector. And Google used eigenvector centrality to rank page. Yeah, it's amazing. It's a very interesting math. How? Well, I can tell you how, but certainly it's a little bit beyond this class. But all I'm telling you is that Google did not beat other people because they got good at marketing. Okay. In fact, they spelled their companies wrong when they try to file the registration. The reason Google killed off Alta Vista, all kind of stuff, Yahoo, whatnot, kills everything is because it uses eigenvector centrality, which is a linear algebra. Okay. So it's not often, but yeah, well, it's a bit more frequent nowadays that something in mathematics ends up changing the whole game, changing the whole business. Yeah, but all you need to know is that with this linear algebra, you are manipulating information. Okay, you're manipulating information. You start with X, and you multiply by A, you get Y. You have Y, you want to know what X gives you that. You take the A inverse, you go back to the original X. You know, you solve a system of equation, all kind of stuff. All this is very doable. And the nice thing about it is, okay, all this looks very difficult because it has a lot of formatting. By the way, my code would look too difficult for you, not because it's all that complex, because I spend time, you know, fine tuning the formatting of colors and stuff like that. If I just want to do multiplication, it's one line. Okay. The reason it has like, you know, 50 lines is because I'm trying to make it look nice. I have a bracket around this and have a color and I have a name. And that takes a while. That takes a while. But trust me, if you want to get something, you want to multiply matrix and whatever, it's just one line. It's that easy. Okay. So this doesn't look easy, but it is easy. A lot of this is just formatting. Because again, I'm trying to write a book. But all this, yeah, you can do in 3 dimensions. See, I can say solve this. Okay, solve this is the same thing as finding the inverse. Find the inverse of a matrix, and just to give you, and this is with this, and we're done. And next time we come, I'll start with calculus. This is my A, right? Oops, sorry. What's my matrix? My matrix. Yeah. A, comma B, comma C, comma D. Okay. Right. You want to know what, if I multiply this to x1, x2, I get y1, y2. If I start with y1, y2, I can multiply by its inverse. Its inverse is given by this. So this is okay. This is what it looks like. I'll tell you what the inverse look like. Inverse of my matrix. See. Okay. Now, and this is the inside. Okay. And this is a little bit difficult to grasp. So watch my hand carefully. Remember, you have three situations in life. No solution, a unique solution, no solution, infinitely many solution. Okay. Unique solution means two equations and two unknown. They kind of like give independent information. No solution, that means they give contradictory information. So for example, if you take A11, A12, you double it and you give it to the bottom, A21, A22, but the right-hand side, you triple it. That's never gonna work, right? Because you double the left-hand side, but the right-hand side, you triple it. So the equation is not gonna work. One has to break down. That's no solution. What's infinite solution? It's when you double the whole right-hand side and the left-hand side, and you get to the bottom, right? So it's a repeat. Well, how do you say that the coefficient of the top line is a multiple of the second line? Well, what you do is you say that AB has the same ratio as CD, right? So, for example, if this is 1 and this is 2 and this is 2 and this is 4, right? It's a double of that, right? So basically, you're checking whether or not B divided by A is equal to D divided by C. Now work in your head. B divided by A equal to C, D divided by C. Okay? If this is equal, you say B, yeah, B times C is equal to D times A. Or AD minus BC equal to 0. Right? So whenever you get AD minus BC equal to 0, you can determine in your head that this is bad news. You either get infinitely many solution or no solution. That's this number. It's at the bottom. So you cannot invert. Okay, you cannot invert, because if you have unique X, you multiply by A, you get unique Y. You can invert it back to X. But if impossible, you can't invert it. So that's why you have this thing, and this is called determinant of the matrix. Now, this is a baby matrix. It's only 2 by 2. Mathematically, you can do this for 1,000 by 1,000 matrix, but you're not going to do it by hand. Okay? So in your problem, you're going to be identifying your matrix. You're going to be trying to find its inverse or whatever. Okay? But you're not going to do it by hand. You're going to use Mathematica to do it. Okay? So sometime you will get system of 1,000 equation. And you want to solve it. How do you do it? You put system of 1,000 equation as an array, right? As a square array. Call it my matrix. And then you say inverse of my matrix. Exactly this, inverse of my matrix. Okay. So in your career, many of you will do this, but obviously not 2 by 2. That's a little bit silly. Okay. It'll be 1,000 by 1,000. Okay. 1,000 by 1,000. Drugs assignment, logistic. Oh, well, it's endless. It's endless. The application is endless. So anyway, I just want to close with that because that's, you know, sort of like gives you the power of linear algebra, but it doesn't give you enough. You know, I haven't talked about what determinant is. I just give you a hint of what it looks like, but basically that's what you want to be working with. I may come back and give a bit more elaborate explanation of certain things in linear algebra, but what I would like to do is start with the calculus. It's a different kind of thing. Calculus in one variable, you're not looking at x1, x2, x3, you're just looking at x. But what's going to happen to that x? In a very funny way, in a very dynamic way. Okay, so I'll see you next week because we have holiday, right? Wednesday and Friday. Okay,ครับ. Feel free to ask me any question. ได้ลูก Okay, yeah, come on. Yeah, fine. Okay, so I'll see you next thingy.